p75, we're going to talk about something called a p-series. P-series are in a particular form. If you look at really whatever you see in the box there, but also the first example or the first set of examples, 1 over n to the p power is the form that a p-series would take. It's just a question of if it's going to converge or not, right, the p-series. So we're going to use the integral test to try to determine if there are any values that will allow this to happen. I'm going to go to Desmos here because what I want to do is come up with an expression that I can use to represent a bunch of different p-series rather than just one. So we're going to let f of x equal 1 over n to the p, so x to the p power. And I'm going to create a slider for p. Now the values that we're interested in here are positive values, specifically 1, 2, and 1/2. So I'm just going to make it easier on myself. I'm going to go from 1 to, I'll go to 1 to 2 in steps of 0.5, just so it's easier to slide along to the ones that I need. I'm going to hit the home button. I want my first one to be a 1. All right, so I'm just verifying that at 1, I'm looking at a positive number that's the highest point along the relevant domain, and that for every point thereafter it decreases. That's true. It is continuous, and so we're off to a good start here. I'm also going to verify while we're here. I'll verify that for p equals 2. Same deal. P equals 0.5. Same deal. All right, we'll come back to that in a little bit. All right, so we're going to let f of x be equal to 1 over x to the p power. All right. And so by the integral test, we would say that over the interval of 1 to infinity, or that we would be looking for the integral over the interval of 1 to infinity, x to the p dx. All right. So then I can take that further. We would let the upper bound be a. So this is all my setup here, just trying to save myself some time and energy down the line. The limit as a approaches infinity of, I'm going to write this as x to the negative p. Oh, I suppose I should put the integral in there first. 1 to a of x to the negative p dx. And so that's what we're going to be working with for each of these cases. So starting with p equal to a 1, then going to p equal to 2, and then p equal to 1/2. That'll just erase the whole thing and rewrite. All right. In the first case, we're looking at a natural log. So the limit as a approaches infinity, antiderivative of x to the negative first is ln of x over the interval of 1 to a. All right, and so that's the limit as a approaches infinity of the natural log of a minus the natural log of 1. Natural log of 1 goes to 0, so we're looking at the natural log of a, which is infinity. All right, so therefore our limit, our derivative, our limit of our derivative diverges. All right, and so we would conclude one over n, because that was a power of 1, diverges
by the integral test.
All right, so 1 down. Integrate x to the negative second,
Negative x to the negative first,
increase the exponent by 1, divide by the new exponent,
over the interval of 1 to a. Find the limit of that. So this is the limit as a approaches infinity. Now this is really the same as saying negative 1 over x. So negative 1 over a minus a negative, so plus
plus a 1 over 1. So just plus a 1. All right. So this is good. I mean, depending on what we define as good. But the first part zeroes out. So this is just going to be equal to 1. So therefore, the improper integral converges. And so we can say, with some slight adjustments to my copy paste, that this integral converges by the integral test.
All right. So then, last but not least,
increase the exponent by 1,
x to the 1/2. Divide by the new exponent.
1 divided by 1/2 is 2.
We're finding the limit as a approaches infinity for that integral over the interval of 1 to a. Look kind of weird, so let me fix that. There we go. So this will give us
2 radical a.
All right, so we get a 2 radical a minus a 2 radical 1, which is just a 2.
All right, radical functions increase forever. So that's going to get us to infinity.
Well,
parent functions that are radical are going to increase forever. So this is going to give us infinity.
And we are, again, looking at a case that diverges. And I left myself with plenty of room to write this, apparently. Let's see. A little resize. A little resize some more. And there it is.
All right. So when it comes to
the conclusions, we can now state,
and hopefully we will be able to use this to save ourselves time and energy down the line by drawing these conclusions now.
If the p-value, if that value was, just go through the different cases, the only instance in which it worked out to give us a converging scenario would be when the p-value is the 2, which is, I mean, if we're looking at 1 as being kind of a cutoff between divergence and convergence, then that could be it. So what we're looking at here is if p is greater than 1, then the series converges. Now, if p is less than 1, that's one case,
I'm sorry, less than 0. Let's talk about that for a second. We didn't do that one,
but let's just kind of reason that out logically here. If p is less than 0, let's say p is a negative 2. 1 over n to the negative second would be the same as n to the positive second.
So that's not a p-series. All right, p-series have to be in the form of 1 over n to the p, where p is a positive constant. And so it's got to be positive.
All right. So with that in mind, we could also draw a conclusion that if p is less than 0, or even less than or equal to 0, it's not a p-series. So then that only leaves us with if p is between 0 and 1, then the series, based on our investigations here, diverges. Right? Because when it was equal to 1, it diverged. When it was equal to a value between 0 and 1, it diverged. There are proofs for this, but this is a reasonable justification. We can apply that by saying, or at least determining, whether we're dealing with a p-series from the word go. So a little algebraic manipulation goes a long way. So 1 over n times 1 over n to the 1/2 would be 1 over n to the 3/2. This is a p-series. All right? Based off of our information here, we can now say this series converges by the p-series test, specifically because p is greater than 1.